However, the increased cross-section allowed us to reduce our bridge's depth. Our chosen design here, it focuses more on the ease of prefabrication and rapid construction. How will we achieve that? This is because of our modular members and a small amount of connections and elements in our bridge. So I mentioned connections. For our connections, we designed two connections, a double shear and plate connection. This allowed us to rotate our bridge smoothly. So that the two insertion points are concentric with the lines of action.
Our construction team consists of one builder and one barge on each side of the restricted island. Bridge construction begins by establishing lateral stability on the west end. Lateral stability on the west end by getting the plate connection between the two footings. The west end crew assembles one panel. Simultaneously, the east end crew assembles four panels, as you can see, before rotating two into place. The south stringer is assembled in a similar fashion. The east end establishes lateral stability, assembles three panels out, while the west end assembles two and a half panels before two panels from the east end are rotated into place. Lastly, our laterals are installed in place to create a sleek and stable bridge.
Yeah, let's talk about some fun stuff now, the money. Okay, these are exciting numbers here, guys. Two builders, two barges, under 10 minutes of construction time. And we achieve a construction cost of 7.32 million. Let's talk about structural efficiency. Using the 11 load combination, we gathered an average aggregate deflection of 0.837 inches, giving us a structural cost of 5.25 million. And then when you accumulate all of that, the structural cost and construction cost, you get 12.57 million in our cost.
Our dedicated team has produced a stiff and elegant bridge that is easy to fabricate and build at a low cost. Designed to meet the latest industry codes and vetted by third-party reviews, it delivers peace of mind from groundbreaking to grand opening. Leveraging proven prefabrication techniques, we shortened on-site construction to keep communities connected sooner.
Okay.
Okay, so this is just more of a general question. What did you find was the rule that gave you the most hassle, that was kind of hardest to satisfy and really stymied what you would have otherwise done? What rule made this, so was the hardest to satisfy?
I would just say the lessons from last year, just carrying forward with the construction costs, all the construction rules. Yeah, from the get-go, we wanted to design to eliminate barges. So that would probably be the rule that was most difficult, because from the get-go, we wanted to eliminate barges. We wanted to actually build in this rotational element, but we also had tight deadlines because we were going to compete in Portland this year. So all our deadlines got pushed up, and the decision-making that went into a lot of stuff was most difficult because of this construction sequence and the uncertainty in being able to eliminate barges, which we didn't end up mentioning.
So if you had more time and you weren't going to Portland or whatever, what would that have changed? What would have the greatest impact on what you chose to do?
It would give us more time. It would give us more time to explore different types of construction procedures. Right? We were trying different tools, ropes, laying on the bridge with a rope. We actually did that. And then several more iterations would have narrowed down our time. When we first started, we started with 3 builders and a barge, I believe, and our time was 18 minutes construction. So then more practice, and a week ago or a night ago, we got under 10 minutes. So practice, right? That allows us to get more experience. That was our hardest thing, getting those bolts in, getting those nuts in, and then remilling all of them. That was our biggest constraint. It's practicality of the matter, not really as much technicality.
There you go. So I saw there's in the design requirements you have two pillars that are offset. Right? Everybody has them.
Yes.
At the end of the in your case, the lateral member was supporting the left portion. It's not at the end of the pier. It's not vertical. What caused you to position that piece exactly there, and what would be the impact of changing someplace or?
Okay, so yeah, we saw that the overhead view of the limitations on where we put members was restricting it. We would love to have gone straight from one footing to the other. That would have violated the overall length limits, and of course, it was also going to be infringing on that vertical plane that's a limit there. So we always knew that was going to. From the get-go, we knew that was probably going to be where we're.
And did it change the members that you have to provide for the truss, or?
Well, if you notice that we eventually actually ended up offsetting our trusses. You see the yellow elements are half trusses, and the red and blue are full trusses. It changed it in that we had to introduce a vertical member right where that plate was. So that would be the answer to your question. That light blue member had to be introduced to accommodate for that. Yeah.
So as you can see in that red snapshot there, you've kind of rotated those diagonals a little bit. Can you talk a bit about why you did that, and had they not been rotated, do you think their performance would have been dramatically changed? What was the rationale for doing it?
So the primary reason for us rotating those, I'm glad you asked that question, is for our fabrication purposes. When we rotated those members, it allowed us to weld more effectively around there, and we also figured it would be more aesthetically pleasing and unique for the eye to see something that's curved. That was primarily our reason.
Yeah.
Okay, so my question is, you have quite a bit of bracing members here in green. Have you considered removing any of them? And if we mandated you to remove some, where would you remove them?
So when we went to go through, we always wanted to consider removing some members, mainly because we wanted to eliminate barges. However, especially during the later part of our analysis, we were finding that the interaction equation with our compression members on the top stringer, the compression and bending equation was starting to encroach on its limits. And that was actually our motivation to keep all of those, because they end up lining up with where our weak points are on our connections, as well as, and that's why we also offset it, so that we could take out the uncertainty that those connections provided in the umbrace.
I'm assuming you used pin at each connection to get that, or?
All I can say about that is we used a pin connection later on in the process, just to see what the difference would be, because we were having difficulties modeling all of those rigid welded connections in our structure.
Yeah, no, that's good.
Thank you so much, guys.
Really enjoyed the real life writers. So that's
All right, everybody.
Bonjour, hello everyone. We are the University of Manitoba Steel Bridge team, and we would like to tell you why our bridge design is the best choice for the proposed active transportation crossing of the mighty Red River in Winnipeg, Manitoba. Our design is not just a piece of steel. It's a valuable addition to the fabric of the city. With its deep color palette and historic geometry, this helps our design integrate with the other iconic bridges of the Forks. For this competition, our focus was on constructability. Our simple but elegant dual chord system features a robust bottom chord, bolstering the simplified geometry and connections of the top chord, improving constructability. Our experienced team also devised an efficient construction sequence, using 2 builders on both sides with the added precision of 2 barges, safeguarding the natural environment. Through collaboration with skilled industry experts and expert mentors, our team has worked hard to develop a bridge that advances the practice of sustainable engineering, making it the absolute best choice for your investment. Thank you so much. Merci beaucoup.
Whenever you're ready.
Good afternoon, everyone. We're the University of Manitoba Steel Bridge team, and we're happy to present our design for the 2025 CNSBC. My name is Alexander. I'm joined here with Tony, Evander, and John. Thank you to the CNSBC, CISC, CSCE, and University of Manitoba for hosting us here today. Today we'll go over the selected geometry, analysis and design, construction sequence, and time and budget of our bridge. We'll start off with the selected geometry. Our bridge has a dual chord system. The top chord resembles an open web steel joist. The bottom chord is arched. The center point of the bottom chord is maximized for depth. This helps us to minimize deflection. Our bridge also has a diagonal bracing system between the stringers. We divided our design team into 3 groups to allow all the members an equal amount of input as well as a chance to learn the design process. On the screen, you guys can see the frame designs they came up with. Each group considered the structural performance for their bridges. They also considered cross-section types, connection types, constructability, as well as complying with all the dimensional requirements from CNSBC. They used a software called SAP 2000 for their design analysis. We also referenced the handbook of steel construction throughout the design process. Each group gave us the values for their deflection and the weights of the bridges. This helped us to calculate the structural cost for those frames. We created a scoring matrix to consider those structural costs, the constructability of those bridges, as well as the vote from the team and advisors to then come up with the design we wanted to go further with. This was the design from group 1. You can see it on the right side of the screen. I'll pass it over to Tony to talk about the analysis and design.
Thank you, Alex. So, our team has worked closely with our fabricator to develop a feasible design for our bridge. To optimize our bridge, we underwent an iterative process by which we adjust the cross sections of each member. This allows us to provide solutions that converge into a final design. Once we have a final frame set up, we then move forward to drafting a 3D model for our connections. Let's start from the top. For our office system, we have selected a double shift connection for both between the top board members and our peers. For our lateral breaking, we opted for a single shift connection instead. This is because the lateral loading is minimal. And the same goes for our load system. Single shift connection on web members, double shift connection on between the bottom board and at the peers. And lastly, from prior experiences, our team has chosen a safety factor of 1.85 for our deflection. This factor of safety ensures that not only will our bridge perform as best, but also our construction team can assemble our bridge with a much lower risk. I will pass along to Evander to talk about construction process.
Thanks, Tony. So for this year's construction sequence, as well as deconstruction sequence, we've opted for a 4-builder team with 1 barge in each river, as well as 1 builder on each side of the island. Our construction sequencing, as well as the construction but in rivers, starts with the piers and the footings, followed by the top board members, vertical truss members, bottom board members, diagonal truss members, and finally the lateral members. And as I've mentioned previously, the deconstruction sequence is the same but in reverse. And now I'll pass it off to John for the time and budget section.
Awesome, thank you, Evander. So we've estimated our construction costs to be $10.7 million. So this is based on having 2 barges and 2 non-barge builders. We've also estimated our construction time to be 13 minutes, then added 2-minute contingency due to any penalties we may face on build day. We also estimated our structural costs to be $6.7 million, which is based on our measured weight of just under 350 pounds, and assuming the worst load case scenario to govern our load case. We're also assuming no load case penalties to exist as our bridge complies with all geometric and structural requirements. This leads us to an overall performance cost of $17.4 million. Lastly, I would like to thank our sponsors of the year. Our sponsors have been a crucial asset to our team and have donated time, funds, as well as materials to our team, and we would not be able to create the bridge we have presented today without them. I would like to thank you all for listening to our team's presentation, and I'd like to open the floor to any questions, beginning with our notice. Thank you.
This is using an HSS. What pros or cons did you experience doing that?
If I may, we know that for our upper system, it carries the majority of the compression load. So we found that having a double angle, which is very strong on that axis, would suit the needs. We are aware that the downside of a WLA is that it does have a weak axis. However, because the lateral loading is minimal, we decided that wasn't a critical factor for our selection.
Extending on that, talking about the top board here, you decided to go with sort of a truss as the top board. What drove that decision as opposed to going with just a solid member?
I can answer this question. The main reason behind this is constructability. This way we can assemble the top truss as quickly as possible within, let's say, 5 minutes, and then not have to hold the bridge anymore. It's self-standing. We can put on pieces one by one without having to hold it again. And another reason, those truss connections also help us stiffen the WLAs along their axis. This way, reducing the unsupported length between them.
Great.
Okay, so you had a slide where you had the lateral multiplier. I think you're going to first take to talk about it during the presentation, and one of them boosts you. So I was wondering how, so depending on your lateral deflection, you get a multiplier to your vertical score. It seems like you guys settled on a multiplier of 1. Is that correct? And how big of a difference was it getting? Can you discuss how you got to that?
The multiplier of 1.0.
Not this one, this is for SAP, right? But for your the lateral.
For the scoring thing, yeah. So we had that as 0.95 in our scoring matrix, and that was just based on testing once we had our bridge assembled. So we were pretty confident that our scoring would be under half an inch for sway, so we used 0.95.
So it wasn't a design target, it's just a byproduct. You're like, oh, okay, so 0.95.
Yeah, we're pretty confident.
I guess I'll ask a similar question that I did earlier. You said that the deconstruction was the same sequence generally as the construction, right?
Yes.
If you were forced to use a temporary pier, not just as an option to maybe be faster or whatever, because the temporary pier has a different cost than a barge, probably all notice that. If you were forced to use one, how would you use it? And how would it change what you were going to do in deconstruction?
It would probably replace the barge, supporting it wherever we can reach, more than likely on the side where the even piers are, because that builder can't reach as far into the river, right?
Yeah, I can also add on to that. Another thing we can come up with is kind of like a jack for the temporary pier, because when we disassemble the bridge, we have to slightly lift it to loosen up the connection in the bottom port. And that's one of the things we can use for the temporary truss, whereas we lift it with the temporary pier. We lift it with a temporary pier, and then we're easily able to disconnect those connections.
Thank you very much.
If there's four criteria based on what the actual results, what's that? Oh, you just look at it. Is there a category for exactly what they're going to get reflection or positive events? Easy to range up there. You don't shoot at yeah, for that situation. And then they're scoring based off of the deviation from one hit, right? That's awesome. They see how there's competition factors. Yeah, absolutely. That's been there. There's not It would definitely be a solution into that. You say that we judge you and make any calls.
From the University of Puerto Rico at Manila West, when we set out to build this bridge, we didn't just think about SEO, we thought about you, the owner. Therefore, let us guide you through on why our bridge is the best for you. We imagine your needs as structured as strong, easy to build, and cost-effective. That's why we prioritize the overall performance. In the real world, time is money, and our bridge saves both. We designed every connection to fit quickly and precisely, but speed alone wasn't enough. We also made it resilient and reliable, ensuring it could carry heavy loads without flexing under stress. No piers are needed when it's time to take it apart, so the island stays whole and untouched from the very start. We cleaned up ports and some benefits shore, our connection was missing, but not anymore. We present a steel pathway designed not just to span the Red River, but to unite the city. We honor the birds and blooms below, as well as the park and pebblers that roam. By being low in height yet high in grace, our bridge conserves this cultural and historical place. Thank you.
Whenever you're ready, please.
Good afternoon, my name is Gabriela Hernandez, and I'm here joined with my fellow teammates Sofia Marrero and Alvin Jaime, and we are the Steelbridge team for University of Puerto Rico at Miami. Our team is made up of 15 undergraduate civil engineering students, and today we're proud to present to you the bridge that we designed, fabricated, and assembled for 2025 Canadian National Steelbridge Competition.
This year's challenge was to design a pedestrian steel bridge in Winnipeg over the Red River connecting the Forks and St. Boniface while meeting structural, environmental, and constructability constraints. Faced with the challenge, we explore multiple concepts and ultimately design a bridge we believe outperforms all others.
For the selected bridge geometry, all team members contributed ideas during the conceptual phase. Through modeling and evaluation, we narrowed our options down to 3: a undersung truss, a double worn truss, and a triple girder truss. Design number 1 was demonstrated good stiffness and weight, however, its high member kept a complicated construction sequence. Design number 2 was lightweight, but it had due to its lower stiffness and complexity. Ultimately, design 3 was selected. It featured efficient bracing, fewer number of members, and faster construction assembly, offering the best balance of stiffness, weight, and construction economy for this competition.
By using SAP 2000, we analyzed all those cases under amplified conditions to ensure reliable performance under demanding scenarios. Once fabricated, critical members in tension and compression were identified to optimize load distribution and minimize internal stress. Precise bracing kept the sway below half an inch without adding unnecessary weight. Our bridge was finally designed with 4130 quality steel, featuring a new double rectangular tubing on the south arch to improve strength-to-weight ratio.
Our bridge features 3 innovative connections modeled in SolidWorks and fabricated from 4130 chromoly steel with a 10,000 pound core steel strength. The first is a rectangular double shear arch connection weighing 0.6 pounds, designed to be completely self-supporting, eliminating the need for tools. The second is a double shear pier connection weighing 0.4 pounds, designed at an angle for a smoother assembly and a faster construction. Lastly, hard-run tubes were used to act as single shear connection along the trusses. These allowed us to significantly reduce the number of members, complying with the composition's emphasis on innovation and performance.
Once everything was welded and nuts and bolts were added, our bridge had a total weight of 183.5 pounds. A vertical load test at a 100% capacity was conducted, producing an aggregate deflection of just 0.83 inches, making our bridge highly stiff, yet lightweight, exceeding structural efficiency.
The construction sequence begins with 2 builders positioned on the west end, while the east end is supported by 1 builder and 1 barge. Leveraging stability between the 2 footings, the west end team assembles 2/3 of the bridge in an upright vertical position. It is then carefully lowered into place, allowing the barge to seamlessly align and connect both ends. This method is possible by taking advantage of the bridge's lightweight design, precise geometry, and smart connections. No supportive tools are required, allowing us to have a total construction time of 9.5 minutes.
For all the construction scenarios, the teams are made up of 1 builder and 1 barge on each end of the bridge. When the island is 3 feet or 4 feet long, a typical method is utilized the construction of the bridge in under 6 minutes. However, if the island were to be 6 feet in length, the north side of the bridge would be disconnected in the middle, then rotated to the construction zone, and fully deconstruction the bridge in 6.5 minutes. Same as the construction sequence, no temporary tool or temporary piers are needed.
Based on our projected time of 9.5 minutes, utilizing 3 builders and 1 barge with no penalties, we estimate a total construction cost of $6 million. Structurally, we predict an aggregate deflection of 0.95 inches and a total weight of 183.5 pounds, with no penalties, resulting in a structural cost of $4.7 million. Together, this adds up to an overall performance cost of $10.7 million.
Our project timeline was divided across the academic year to ensure steady progress. Summer was focused on mastering software tools. Fall was dedicated to prototyping and selecting our final design. Winter involved fabrication and turning concepts into components. And finally, spring was focused on refining construction techniques and preparing for a presentation.
Our bridge is not just a product of careful planning and hard work. It's a competitive structure that showcases the best of engineering design, innovation, and performance. On behalf of the University of Puerto Rico, thank you to the University of Manitoba, the CNSBC, and the CISC for making this competition possible.
First question. I noticed you looking at your design. You have a estimated weight to total weight of 143 and 106 pounds. And in your final design, you had a weight of 180 pounds. Which seems like a significant increase relative to the theoretical. Where do you attribute that to come from?
Yeah. Well, the first initial weight is in SAP 2000. This is not including welding and nuts and bolts, as well as our own fabrication. So we take that into consideration when we do the weight of the official design.
This seems like a large amount of.
A lot of welding.
Yeah, we welded ourselves. So.
Okay, so I have two questions. The first one, just so you said you use 4130 steel. Is that for the entire bridge, or is it just for the members themselves?
Yeah, this is for the entire bridge.
So even the connections are in 4130?
The member as well as the connections.
Oh, okay. So I was gonna ask about welding, but it doesn't apply since it's the same steel. Anyways, yeah, because I know it's always a hassle welding these things. So I was wondering what precaution gets used, but yeah, it doesn't apply. So second question, I've noticed, and I think you're one of the only team that have done this, is you have an asymmetric bottom board section alongside the short side. So yeah, can you elaborate? How did you decide on this bigger section for your long stringer?
Yes. So for the sub stringer, since it has a longer span, it was more. It could have had more sag and buckle, so we opted for that double rectangular tubing. We designed the north side as well, but we noticed that for the strength to weight ratio, it added too much weight for the little stiffness that we got. So it was more optimal, since the north side is shorter, that we can just do a single rectangular tubing.
And do you assume that the loads share equally between both stringers, or how do you model this difference? The load, the angle loads. Do you assume it's equally spread between both sides of the bridge, or do you assume one side takes a bit more? How do you?
Yes, we on SAP 2000 we do a virtual workforce, and we evaluate every single member, and we distributed the loads as best as possible, so it wasn't an issue.
Thank you.
I'm intrigued about the piers that are supporting the bridge. You seem to have double members, and since the weight seems to be very important for your team, why do you have such a?
Yes, so one of the reasons was for stability, and as well last year we had an additional member, diagonal member from the pier to the beam. So to reduce those members, we combined them. So now the piers acts as the vertical as well as the diagonal member. So it acts as both jobs.
But do you see significant load into this small angle?
Yes. What we did was we did that in X as, and we expanded the arc. So last year the arc was more shorter, so we did was the leg is more shorter, and we expanded the arc. So we had the span was like.
I got a kind of a general question. We kind of played around with the idea of rolling dice to change the shape of the deconstruction area. We did the same thing last year, although that didn't really have a massive effect. We try to do it again this year, but it doesn't seem that anybody's really cared that it might change. Everybody's approach has been the same. Do you think if that rule was expanded or changed, it would have changed your approach again if it was impossible to reach, or if the construction zone got dramatically shorter? Like what would have been your approach if it just completely took away the approach you're taking now? What would you have done different?
You mean like not using barges, or
because we shrunk or expanded the island or the river, and it doesn't seem like we did that enough to change people's minds to do something different for deconstruction, which we weren't necessarily trying to do. We just wanted to foster maybe innovation with a different approach. Some people are using temporary piers, some people are not. Did you find that rule had any impact at all, or no?
Yeah, it was a little challenging, but we figured out our own construction sequence as well as the construction sequence. But I say that if the span was way larger, I say that the optimal solution would be a more simpler bridge and use and construct it in the most fastest way possible, so that the barges don't, the time is not going to be an issue.
All right, thank you so much.
Maybe that just maybe put a good card. Okay, the part we can change the links and we have not to be like this. We can try to go to and we want to talk to me for almost 3,000 things next year. Like we are spare, we can more challenging concerns or just keep it generally the same. Challenging a little bit amount of challenge, but they just get ready. Like we got to figure out all the control. It would be like I wish I would be there. I think we need to figure out Mr. Banks. Yeah, we can take it harder.
Whenever you're ready. Thank you. Whenever you're ready.
Okay, so designing a bridge that is going around a ecologically and culturally symbolic feature like the Red River in Winnipeg is a task that's pretty challenging. So our team is proposing a well-designed and kind of aesthetic bridge to meet both public requirements and environmental requirements. For us, our bridge weighs only about 160 pounds because we prioritize lightness. This is important because it reduces the material use, it reduces the total cost, and the emissions that are done through construction, which is better overall. We also tried to prioritize stiffness, and this was achieved through angle connections and which were double bolted, which improves the overall structural rigidity of the bridge while reducing the long-term effects of fatigue. For constructability, we kind of went with more of a practical, simplistic approach, because why reinvent the wheel? And we went with 2 barges and 2 builders. Barges because it provides easy site access and storage for construction and deconstruction. And this goes along well with how our bridge is segmented, because the takedown is simple and minimally impactful, and the material can actually be recycled at the end of its service life. And finally, for the aesthetics, our bridge features an underslung arch with some trusses, and we think that blends in well with the nature around and is sorry, is good for the city and blocks. So we believe that with our structural efficiency, our sustainability, and the nice aesthetics that we have, that our bridge is an ideal choice for the city.
Hello, everybody. We are the University of Saskatchewan Steel Bridge team. My name is Danielle. I'm here with my colleagues Brandon, Rachel, and Isabel, and we're going to show you our 2025 design for the Steel Bridge competition. This year, the city of Winnipeg has requested a new pedestrian bridge to span across the Red River and connect the Forks to the St. Boniface areas. Since there is an island in the middle, we have been asked to protect wildlife and vegetation by minimizing our ecological disruptions and maintain the natural beauty of the area while also ensuring safety of the paddlers and those using the park. Our team specifically chose to focus on stiffness, lightness, and constructability, as Ashton said. Our analysis was conducted in S-frame. We considered the different loading patterns based on the rules and analyzed the deflections to see where we could improve our design and if we needed to make any changes in member spacing or size. Additionally, our team considered the connection design to be a crucial item to minimize the deflection. The analysis was used to estimate the deflection prior to load testing. Our team members came up with several designs, many of which included composite stringer members, tension development members, and truss footers. For this stage, we focused on the geometry of the bridge with detailed connection design to follow. For this, we began optimizing the design for construction, including refining our connections, opting for tension plate connections, compression wedge connections, and detailed design of the understructure and lateral connections. Overall, our primary objective in designing our connections was to maximize stiffness and constructability. The final design consists of 7 lateral load-resisting elements, a keyhole footer connection, in conjunction with compression wedge connections to again work towards our team's personal goal of maximizing stiffness. We also refined our geometry to work cohesively with our finalized connection design.
So yeah, like my friend said here, we wanted to design with their constructability in mind. So we wanted to start with the 2 east and west footers and include the east and west stringers just to keep the barges active while the builders are running pieces. We then wanted to place and connect the outside laterals and get those footers established to improve our rigidity or structure, so it could stand up on its own. Then we want to complete the northern truss to have a freestanding bridge, northern stringers to have a freestanding bridge. And then we follow up with the southern stringers to get it all together. We then want to complete the northern truss, starting with the bottom board and then connecting the vertical pieces to the stringer, and follow the same approach on the south side, starting from the outsides and working our way in. And then finally, we want to put the laterals in, again, starting from outsides and working our way in, trying to keep the barges active while the builders run pieces. And then in terms of deconstruction, it's ultimately the exact same process, but in reverse. So then, for construction economy, we started by running through practice construction a few times to get a rough estimate of time. And then we used the specifications in the handbook to calculate the ultimate cost of what that would be. So we allowed ourselves to about 19 minutes and 30 seconds to construct it. And then we're estimating about 3.5 minutes of penalties, worst case, to get a total time, 3.5 minutes of penalties to get a total time of 23 minutes. So our ultimate construction cost is estimated to be about 16 million.
Likewise, our structural efficiency was determined using our measured weight of 161 pounds. Aggregate deflections for all load cases were determined using our S-frame data, and they were verified and corrected with a 100% N6 load test. The maximum structural efficiency is 5.6 million. And then summing those costs, the overall cost of the bridge, worst case, is $21.7 million. For the design and build of the bridge took about 1,750 person-hours and cost about $6,500 out of pocket for tools, hardware, load testing, and construction-related materials. And then the steel was donated for the prototyping and fabrication, and all the fabrication was done in-house. The connections were both milled in-house and laser cut by a third party.
So thank you, everyone. We'd like to thank, of course, our team, everyone here in Winnipeg and everyone back home. I'd like to give a shout out to all of our sponsors who make this feasible, and then, of course, University of Manitoba for hosting, and the CNSBC competition.
Okay, I got a question. Can you go back to the load test slide showing the full load test? Okay, so you said you did a 100% load test on N6 to verify things, right? So can you walk us through what actually happened? You did the stuff in SAP, or when you said you used S-frame, and then you did this, and then you looked back at it. What were the differences? Did you then tweak things in your program to kind of have it align to see how far the other ones were away? Like what was the process after you did this, and what other changes, if any, did you make, and why?
So we didn't end up making many changes because our model was relatively close with our actual load test. Just the way we modeled it, it seemed to be pretty accurate. I think we got about, it was the same, but a little bit less. So we got about 2.5 or 0.27 inches on the northern side, and then about 0.67 inches on the southern side. But then in reality, our actual load test, we got about 3.3 on the north and about 0.9 on the south. So it was pretty closely aligned. And then from there, we kind of tweaked all the other load test cases, and to get a relatively accurate estimate for the structural fit.
You probably said this, but what kind of safety factors, if any, were you using to initially get your deflections?
I'll let Parker get some.
Yeah, we were kind of going for about a factor of 1.2. So like all our design stuff, like we were looking for about 1.2. Like we were trying to push that limit, but like I guess we were also verifying with like in-house testing of different members, like connection and pieces, to kind of verify that like they're within the specified like strengths needed and went with it.
Inspiration. Need inspiration. Mm-hmm. Let's flip through. I had a simple question. You all have four similar piers at each corner of your bridge. We know the piers are distributed. There are two that are further apart than the other. My question is, do you have the same reaction, the same load on each of them, or is there the best load and depending on the case?
They're definitely not the same, like, and we know that, but it's just kind of for the fabrication of the bridge, just stuck with the same thing, just to kind of keep it simple. And like, I guess so we have to order less materials and just kind of keep the same, but knowing that like they're relatively small reflections, and like it shouldn't impact the overall performance of the bridge too much. So we kind of just, for simplicity's sake, just kept it all the same.
Yeah, and to build that, this is kind of a good representation. If you look at the underslung truss on this picture from the side view, the trusses pretty much line up all the way to the last string on the north side and the last two strings on the south side. So part of that, or keeping the materials the same, was to make it look better aesthetically, keep it as symmetrical as we could, given the skewed footer boxes this year. And yes, another thing we did to kind of mediate that is the material in just the bottom girder of the truss on both sides is 0.1 inch thick, whereas the rest of the material is all 0.065 inches thick. So.
So in deconstruction, this year we gave you the option for a temporary pier or barges. Can you run us through how you determine on your deconstruction solution and deciding on barges versus this pier?
Well, ultimately, we just wanted to keep hands busy because we know the barges can't exit the water and the builders can't go in the water. So we figured, practiced and figured that the barges can be taken apart pieces and handing them to builders who can run them. So just to keep everyone doing something the entire time to maximize efficiency, we went with barges in the river.
If you load your bridge, the maximum, at what point or what the element will fail?
Actually, can you flip through the connection? Secondary general. Yeah.
So you see the connection on the very right-hand side there, along the bottom of the truss, on the understructure there, the under truss. That's going to be one of the ones just in the middle there. That's going to pull apart first. So we did some rigorous load testing, and we had to change bolts at one point because we were, I guess, took some really 3/4 inch bolts and welded them onto the edges of those wedges there and pulled them apart in the press there. And we know we're pretty confident that's going to be what breaks first, based on all the testing we've done.
In this picture here, we actually were able to load test a lot of our connections to the max and get a relatively accurate value. So we load tested some pure tension, some pure compression, some to make sure both. And we either resize bolts accordingly or figured that we would make sure factors in the metal or the part of it.
There's a factor of safety you use for your connection, or with the knowledge that you have with some of the tested.
That was about the 1.2 factor there we were using.
There's also
yeah. I guess the 1.2 factor was mostly for connections because that's kind of our critical point.
Cool. All right, thanks, guys.
One email address I sent to Grace.
So with your team? So yeah, you have USB or? Because it takes a long time to get on my system.
We have USB.
Yeah, USB.
That's the translation.
Oh, just trying to get out of the translation.
For sure. Hopefully you can find that information, like all Sheila and it's still going to actually send that the racket tank declutter the interior. That's another issue. It's not probably already Because there is.
Okay, when you're ready, guys.
Imagine a bridge that doesn't just connect Winnipeg's important communities of the Forks and St. Boniface, but does so with efficiency, elegance, and environmental sustainability. The University of Waterloo's proposed Red River crossing connects the communities of the Forks and St. Boniface and provides accessibility and safety to its users.
Our primary focus is structural efficiency, which strengthens our sustainability. By using lightweight members with optimized structural forms, we minimize cost and material use while maximizing our performance. With this, we also have better fabrication and lower environmental impacts. With a lightweight structure and innovative connection members, we prioritize circular engineering while while minimizing disturbances to the environment.
Our proposal is more than just a connection between two communities. Our design is a bridge between structural efficiency, environmental sustainability, and also cost-effective engineering, and we are confident that our design is the best choice for the Red River Crossing and the citizens of Winnipeg. Thank you.
Are you ready to go? Or?
Yes. Yeah, whenever you're ready to do.
Right. Good afternoon, judges and competitors. I'm Musa. I'm Blake. I'm Kafka. And we're representing the University of Waterloo Steel Bridge Design Team. We are very excited to present our proposal for a bridge connecting the Forks and St. Boniface and Winnipeg. A little bit about our team first, though. We are representing the University of Waterloo. We have 20 active members, or roughly 20 to 25 active members from civil, architectural, and mechanical engineering. We have been participating in this competition for 11 years now. And at this point in our team, we are really at a transitional point for our leadership. So we decided to take that as an opportunity to experiment with new design methodologies and really focus on objective design. So Blake will talk about that a bit more, but first we'll talk about our design goals. So our main goal here is to better connect the trails between the St. Boniface and the Forks areas in Winnipeg, doing that by crossing over the Red River. Obviously, we want to do this by creating an aesthetically pleasing design, but we also have the goals of minimizing cost, minimizing ecological impact in the Sandbar Island, as well as minimizing the life cycle impacts during deconstruction when the bridge gets decommissioned. So now I'll hand it over to Blake to discuss the design more.
So the first method, the first thing that we did, decided to go with an undertruss, of course, because the overtruss configuration this year, the load path was too long, in our opinion, to get an effective overtruss. And it's easier to analyze than undertruss, so we went with that as well. And previous bridges we built off of. We narrowed the geometry down to modified Pratt truss because it keeps the critical longer members in tension, and then the shorter members in compression, so less buckleability of the members. And the modified version is the Sandbar Island. We have limited our connections really by modifying the Pratt truss. We began our analysis first by experimenting with different truss configurations in SAT 2000. The main ones were the Pratt, the Warren, and the K-truss. We then had our bridge configuration, and we created a script in MATLAB that essentially computed the theoretical deflection of each bridge combination. So if you take the cross-section of each member and change them, it computed over 60 million combinations of different member cross-sections and got the theoretical deflection and the theoretical weight. We then calculated the structural costs of these cross-sections and took the configuration that had the minimum cost. You can see here in this graph is the non-inferior points of that analysis. So there's about 3,000 points there out of the 60 million. And this was an iterative process. So essentially the MATLAB script focused on the longitudinal numbers. And we had to iterate in SAP 2000 for the vertical bracing numbers. And so how we did that was we used the effective moment of inertia of the longitudinal numbers and assumed that the bending stiffness would contribute to a bending deflection. And then there would also be a shear deflection from the vertical bracing numbers. We then used SAP 2000 to get the theoretical deflection of the entire bridge, that calculated the shear deflection coefficient, and redid the analysis in MATLAB again. And we iterated that about 20 times, and we were able to come up with our final bridge configuration. We then did a detailed analysis in SAP 2000 for buckling in torsional and lateral directions. And for connections, we just use simple gusset plates for constructability. Here is the results of our analysis. Our low case N7 was the worst case, with an aggregate deflection of 0.94 and a weight of 220 pounds.
Okay, so sequencing is fairly straightforward. We start with the main span, or the stringer and the footing. Build the moment frame over on the west side, I believe, at the top of the screen there. Then we move on to the vertical members, highlighted in green. Then on to the under truss, highlighted in red. Then the diagonals connecting the stringer to the under truss, highlighted in blue. Finally, our lateral members, last moment frame off the bottom here. And deconstruction is the reverse. So we start with these laterals, move on to the diagonals, under truss, the verticals, and then stringer. So this brought us to construction and time economy, so of 20 minutes in construction, and that an associated cost of 15.6 million. In the reverse, that deconstruction is about 12 minutes with a deconstruction cost of 8.28 million. Yeah, and then the number of builders, we have 4 builders, 2 barges, and 2 builders on land, 2 on each side, basically. In terms of the project time and budget, we started in August, actually. We started before the rules release, just setting up the scripts that Blake mentioned in MATLAB and whatnot. That conceptual design took us to about September. We moved on in October. Structural analysis took us to November. Drafting started around winter break and ended just as we came back with the new year. Fabrication took us pretty much all of 2025 from January to April, and that left May for construction. And then, here we are. In terms of the actual cost of this project, fabrication is what took the most of it, at about $3,400. Hardware was only about $50, and the steel itself was $1,100. Yeah, that's it. Thank you so much for listening, and welcome.
I have a question about your MATLAB thing. Can you go back to the...
Sure.
Okay, so you said you ran scripts of like 60 million iterations or something like that. I don't quite remember what you said. Can you just elaborate on that a bit? Did you do that after kind of optimizing some things to do like a super ultra optimization? Did you do that like right at the beginning? How did you leverage that, and why did you do it like that?
Yeah, so the optimization in MATLAB was done later than we had hoped. So we tried to first optimize the best we could without MATLAB and kind of give us some constraints, or else we would be computing forever. So we decided that this modified K-truss is the configuration that we wanted to go with. And all that we were changing was the cross section. And we had to realign the centroids to fit the maximum member sizes, of course, and the clearance at the bottom. So what we ended up doing is we the MATLAB script basically aligned the centroids of the members based on where they would have to fit in the bridge envelope, and then computed the effective moment of inertia. And then using the effective moment of inertia and the theoretical curvature, right, of the bridge, it was able to compute the deflection based on bending only. And then we assumed, since there was some discrepancy between the theoretical, like the moment version of the bending deflection and the SAP 2000 results, we assumed that that was based on shear, like based on an imperfect connection of the longitudinal members. So we then used that constant to calibrate our model and ran it again, and just kept comparing that to our SAP 2000 model until we got it perfectly calibrated.
Okay, so if you didn't have that tool at your disposal, what would your gut have told you to optimize where and why and how? If you just had to go off of, gut feels.
Yeah, so in previous bridges, we've had to basically be more subjective in our design and choose what we think would work best. And we've typically went with HSS numbers for the most part. The one key thing that MATLAB was different than our gut feeling is it told us to use double angles on either the top chord or the bottom chord. We chose to do it on the bottom chord because those are tension numbers and much easier to design for a double angle. But it makes sense intuitively because the moment of inertia is based on the distance of the material from the neutral axis. So having essentially a flange was able to sit in our bridge, and that was the main difference.
Okay, so a couple parts here. So how heavy is your bridge?
220 pounds.
Okay, so when you're talking about the economies of your bridge, you see that fabrication is a significant portion of the cost relative to material. And given you get so much optimization in order to reduce that amount of material at your design stage, do you think it was worth it? Or do you think that you could have gotten a better economy if you had used more material, but in a more fabrication-friendly way?
Yeah, so the main optimization that we did this year was based on structural costs. And I would add that even considering more constructability costs alongside this would be an next step for next year, because there's some of our connections are a bit complicated because of that. And then from a fabrication standpoint, we always make sure to have enough funding to get the material, right? So we're more worried about like our overall costs and performance. So we wouldn't use more material to lower the fabrication costs. Maybe the fabrication time, if that would increase our construction speed.
So you're saying that you're worried about costs, so you want to use
We're worried about competition costs, not the fabrication costs.
Are you not considering fabrication costs in the costs?
So maybe I can step in. So we are. Big thing with our fabrication, we do it professionally on campus as well. So that's the big bulk of it is the labor. The actual materials to do the fabrication is not that much. It's the labor cost that where that 3,000 whatever comes from. Kind of what Blake was saying. Yes, we're concerned about the costs of what it takes to actually get the bridge here and assemble it for you guys. But we also want to come to the competition and do very well. So if for us that trade-off between, okay, it's going to cost us a little bit more to fabricate, but it also means that we're going to save cost in terms of the scoring at the competition. That's a trade-off that we're happy to make because we want to prioritize our performance here versus, we can always just find more sponsors or make our. But for us, that's priorities: coming here, being competitive, and hopefully having a pretty good bridge.
Okay, so your point is that the fabrication cost to you is not a factor in the competition, it is the actual weight that's being used for the competition.
Yeah, how it affects the scoring here is what we're concerned about, not so much how it affects the cost again. Yeah, exactly.
Yeah. Well, my question is, so these optimization tools, now that you've gone through the process of doing a nice MATLAB script, running it, and building a full design with it, how do you look at it in terms of time spent doing this versus time spent doing construction practices? Because I saw you only had a few weeks So now that you look back, would you prefer cutting down on this and spending more time on construction, or do you think that tools like this have a lot of value?
So the way we looked at it this year is it is a tool that we can reuse, right? Recalibrate for next year, for years to come. So it was a bit of a trade-off. We had less time for construction, and I think that was more of a result of some issues in our initial fabrication. As you see, we started fabrication in January. So the bridge should have been fabricated and ready to go at the beginning of or middle of March-ish. And so we should have plenty of time for construction, but there were some key errors that we had to get fixed. So that was not really a function of when we all of the time that we spent in the design. It was more of some key mishaps that kind of hindered the fabrication for this project, because that's typically a lot shorter.
Makes sense. You guys still have got your design up. Makes sense.
And we have staggered the design for next year's competition to be earlier.
Okay.
So that
Part of it was the also development process. And we're going to continue doing that after this competition throughout the summer. It's just really refining this tool even further and building a process that we can go about. So really, this was an investment in this year. And what Blake said too is our long fabrication was kind of independent of our design process. Like you said, we were planning to have had it done for the American competition in April. But that was independent of it. Ideally, it would have taken shorter, but still, regardless, we did spend a little bit more time designing this year than we would have last year otherwise. And we find that that's an investment for future years when we're gone, however many years, they'll still have the tools to succeed.
That makes sense. Thanks.
That's what I like to hear. It's all about transferring the knowledge to you, and really. So thank you so much.
Thank you so much.
I was in French as a student. We were so I wanted to see it. Spend all the time. It's cool back here. I don't want to go back out. Yeah. Yeah. It's construction right? Yeah. To get an American they were also pretty sure it's making a small plastic.
Hello, everyone. My name is Isaiah, and I'm representing the Western Ridge Steel Bridge team to tell you about our solution for connecting the Forks and St. Boniface across the Red River. For our design, we prioritized aesthetics and constructability to ensure that our bridge flowed seamlessly with the Winnipeg's iconic river trails. Our under-truss design will ensure that our bridge does not impede on the sightlines for park users and paddlers, while still flowing in the region. The large prefabricated sections, along with an innovative connection design and efficient construction methods, ensures that our bridge has minimal impact to the environment while having minimal construction time. This bridge is strong and sustainable and built with deconstruction in mind to ensure that it is fully sustainable throughout the whole life cycle of the bridge. In short, our bridge respects the land, the people, and the future. Thank you.
Are you ready?
All right. So in case you guys forgot, I'm still Isaiah, but I'm joined with Matt and Brian, and we will talk to you a little bit more in depth about our design. So our presentation is divided into 5 categories, starting with a detailed description of our design and analysis, and then going into our construction sequencing and our budget.
All right, so going into our consideration of alternatives, based on the rule set provided by the competition, we considered 3 different alternatives: a pony truss, a modified side truss, and an under truss. Based on preliminary design, we immediately eliminated the pony truss due to fabrication difficulty, a high member count, and connection difficulty. Moving on, we did static analysis on a simply supported beam and determined the shear force diagrams and the bending moment diagrams based on each load case, making for a total of 11, then overlapping them to create the envelope, and continued our design in SAP 2000 for modified side truss and an under truss. So we made some basic assumptions to make sure SAP wasn't just giving us numbers we couldn't trust. We assumed build time is directly proportional to the number of members, and based on build times from previous years, we divided total build time by the number of members to determine the time per member. We use this going forwards in this design as a reliable for the construction cost. We mapped the nodes on SAP 2000 to measure points of deflection inside of our SAP model to give us decently accurate deflection costs, and we exported these results to a spreadsheet shown below. So moving on to the side truss, we split our design side truss and under truss. Inside of SAP 2000, we saw so many connections, it's just not going to be feasible. Although it has a low deflection, it just leads to a high overall cost due to our high weights and long construction time. So we concluded with the side truss, and we began optimizing the cross-sectional areas. We considered different lateral designs, but we ultimately decided that the trade-off for a little bit higher deflection, but a much lower weight and much quicker construction time was worth it. So we present to you our under truss.
All right, yeah, moving on to connection design. So a large part of our connection design for this year was inspired by last year's connection design. One of our two main issues were that we had our compression bolt in shear. This was inefficient as it caused the bolt to be bearing the force that both members did. And then our tension bolts were drying, and they caused eccentricity. So in order to fix this, we essentially flipped the connections. So our compression bolt is now normal to the surface. This just allows the members to be resting on each other, just transmit the load straight to the compression. And then we went ahead and milled our own tension pieces, so a very easily reproducible part that we could do in our shop at home. And that would allow for no eccentricities to be created in tension. Now just going over the actual connection design. We just considered a few different cases. So we got our net areas in shear and net areas in tension. And we just checked a bunch of different cases. So we looked at our tensile failure, block shear failure, as well. We considered bearing failure. Yeah, moving on to construction sequencing. So we designed a new member that's just for construction. We call it our stiletto. So our construction composed of two barges and 2 builders. We go ahead and place down our stiletto, and this allows us to build up our stringer vertically. This is just saving time for us at the beginning. After we've built our members vertically, the barges are then able to lower down our stringers and connect them in the middle. After our stringers have been connected in the middle, we are then allowed to install our columns on the side, ensuring that we don't violate any of the restrictions. And this raises up our bridge, allowing us to put in our bottom chord as well. For deconstruction, it's the exact same process, but in reverse. Yeah, we have a predicted construction time of 17 minutes and predicted deconstruction time of 8 minutes.
So for our total project cost, it comes to just under $21 million. We came to this by actually load testing our bridge. In load testing our bridge, and we found the deflection was 3/4 of an inch. Our actual construction time during practices was 17.5 minutes. And yeah, that's all. So thank you very much.
I like how you ended. Okay. Okay. You said you load tested it.
Yes.
Did you do anything to the design after you load tested it to optimize anything, and what did you do, or did you have time?
Yeah, so once we load tested, so we actually calculated, I think it was 0.6 inches. And then when we load tested and we got that it was 0.75 inches, we found that was well within reason, and there wasn't any modifications that we could have done to actually reduce it any more, that without adding any more members or weight to our bridge.
Okay. Getting close to exhausting all of our questions. The last team's gonna have it real easy.
The down factor, exposed vertical deflection score based on lateral deflection test, how would that come into the equation when choosing your bridge geometry and design?
Yeah, just the lateral down factor.
Yeah.
We did like a preliminary lateral testing to sophisticatedly made up lateral fetches based on what we've done in previous years, and we found that it would be a 2.5 inch deflection. So that just ended up being 0.95.
And you reached that with the real bridge.
Sorry?
You managed to get the 0.5 deflection?
Yeah, we were under 0.5. I think when we did it, we were at 1/4 of an inch, but we weren't too sure about the actual load in place. It was roughly around 75 pounds. We predicted per hour.
I see.
So based on what you've seen from all the other teams here today, and at the aesthetics judging as well, would, like, for next year, if it was the identical rules, what would you add or remove based on what you've seen other teams doing, either innovation or optimizations?
I think construction is definitely like the most costly thing for the bridge. So I'm interested in how some of the other teams have been able to get their string across so quickly. I don't know if they're within the rules, but just improving.
Oh, do elaborate. We'll see tomorrow.
Yeah, because I know construction portions have to start within the footing, so I'm going to show us more. But yeah, just improving construction. We'd like to improve our stiletto a little bit more. We found that it's still pretty wobbly, but if we could get it completely freestanding, allowing us to build vertically and basically making the non-barge just a runner and allowing the barge to do all the building, that would be probably what we do for construction.
I guess similar to another question, if you could go back to the isometric of your bridge,
which one?
Yeah, whichever one shows the whole bridge. Where do you think the bridge would fail first if you were to load it to failure, and why?
Yeah, it would be the last web members of the top were the ones closest to the down here. Yeah, great.
And why?
Just because there's quite a bit of compression going into those web members. Yeah, there's a lot of optimization that we tried to do with the web members, like making it very, very narrow because there's not a lot of force going through a lot of them. So we tried to make them very, very small, but for ease of fabrication, I think some of them we kept loading and loading and loading it. Those would be the first to fail based on how we optimize those. We stopped those two, just so I think both of the compression coming down to those spots.
Yeah, let's say we gave you our job of writing rules. If you had one rule that you could change, what would it be and why?
Yeah.
Skyhook.
That is actually a question. Like, we always encourage you guys to give us your critical feedback, not whatever you want to call it. Like, we write the rules every year, so if you have any suggestions, we are legitimately very, very interested in hearing, for real. So please come see us at some point and let us know. We just try to make it better every year. So anyway, thank you very much.
Thank you.
Oh yeah, totally. Totally not on. Yeah, totally not. Yeah. Thank you for the applause. It's really needed. It's really needed. Basically, since this is our first year, we just tried to make a design as strong as possible because we didn't really know about like everything that goes on in the competition, how the loading is going to be, and we wanted to make a design as conservative as possible. So we went for designs that we could find in the Steel Handbook, the Steel Design Handbook. We've looked for members that we could find pretty easily, where they had all the member like designs, like the calculations done, so that we know that would be safe in different loading conditions. And then for our overall design, we just went with something pretty simple. We tried to do it simple. We had a bunch of prefabricated members with a bunch of welded pieces welded together in order for our design to be built quickly and effectively. And yeah, of course, it was very tough, blood, sweat, and tears into this competition. So yeah, this bridge kind of represents perseverance and never give up. So yeah. Yeah.
Our bridge is comprised of 11 welded members and 6 steel bars that are connected. We chose this over our original designs because of the ease of constructability.
Yeah.
Initially, we wanted to have a triangular, welded members.
Yeah.
Because of the size, because of the strength. It's obviously going to be significantly stronger, but we found it very challenging to find welders that were willing to
do it, and also like design is very difficult.
Yeah.
So we just went with something more blocky. So all of our pieces are pretty much rectangular, and we have just diagonal members just welded in between for more support in all your forces. Okay, so this is our analysis. We worked with WinPro because it was something that we could do, I guess, most quickly. So we did all the analysis one by one. We put the loads down, and we found the maximum normal forces and fluxions. For the analysis, we did member releases at all of the joints to kind of not factor in for rotation, which would significantly increase the amount of normal forces that the bridge would experience. So for example, when we did have moment releases, the forces that we saw were maybe 10 kilonewtons, but with the moment releases, it got up to 70. So it's kind of something to do for strength and also just safety overall, to make sure that it wouldn't fail from strength specifically. Okay.
Construction and deconstruction. And we start with first assembling the endpoints, and then we connect the side members until the middle, and then
we use the middle connection on both sides, and then the two member supports are connected in the
Yeah, and then for deconstruction, it's basically just like with most teams, same process but reverse order. And for time and cost, so we're being optimistic with like time to build it. We're having 4 builders, 2 barges, because it's the first year and we wanted to have all hands on deck. And also if we have more people, we can kind of build a bit quicker. So yeah, we assumed 4 builders, 2 barges for a cost of $15.3 million for 50 minutes. We didn't do the actual calculations for deflection, so that's kind of our cost, but let's assume 10 million extra, so like I guess 25 million total. And that's a conservative estimate. And thank you for listening. It's a short presentation.
What's your perfect Sunday?
Perfect Sunday. I mean, for us, it'd be more than an hour and a half of sleep.
Yeah. So, I got it. So first of all, thank you for coming here. Thank you for being here. Thank you for your perseverance and trying to push through and get this bridge built. It's very motivational to see that. Yeah. Let's give it up. We always have teams that sign up and don't show up, so I'm very happy that you guys did show up and own up to it and are trying your best. It is
for us, it was kind of just financial because like when you're doing registration, like registration is in February and March, and it's like at that point you can't really back out. And so it's kind of like basically if you were to ask me last Tuesday if I wanted to come here, I would have said hell no. And it's not even because of like just everything. It's like last Tuesday we did not have a bridge. Like I'm being honest, we didn't have a bridge because we got our steel Tuesday morning, and basically we had contacted people to weld. They saw the amount of steel we had, and they said we're not welding this.
Run all over the GTA to find a welder.
So then we got a welder last Thursday. They welded for us in one day. So we got our members welded on Friday morning. So yeah, it was very to the wire, and we're totally not working on it right now. So, yeah. Yeah, it's been really tough, and I'm not kidding about blood, sweat, and tears. It was blood, sweat, and tears. Yeah, so we've been working really hard. We hope to do it. Yes.
Okay. So we've seen a lot of bridges today.
Yes.
We all acknowledge the game today. If you could make one change to your bridge, what would it be?
One change. Are you talking about like our actual design, like what we have here?
I've seen like 15 bridges here today.
Yeah. I guess like for our members, we could have made them like smaller and thinner, because like we chose what we could find in the steel handbook, and that only went down to like 1.5 inches in like width and like 1/8, I think 1/8 inch in thickness. We've been having so much trouble drilling. It's hell. Yeah. So basically, like, if we were to do it next year, like what we would change, it'd probably be maybe more members that are a bit thinner, because it's like when you're trying to like when all our main components are gusset plates that we're connecting with nuts and bolts. So like everything has to be drilled through, and drilling through can be like very like demanding mentally and physically, and also like material wise, because like we've gone through
7 bits.
Yeah. Like we literally dulled them down because it's so much drilling. So like next year we would probably just try and get like for our main members thinner and smaller, and then for like our inside components like our welded pieces, making them thicker, because as you saw like earlier today, our welded members are very thin. So like if we had thicker members, they'd provide more support, and that would overall make a better bridge. So thinner main members, thicker inner members.
Theoretically, we want to also attempt a more complicated design.
Yes.
We were very safe and conservative with
Very safe this year, but it's like we're
I'd really like to attempt like a triangular.
yeah, like we're almost gonna start basically as soon as we touch down at this point.
Pretty much.
So we want to run it back. So.
Well, be careful because the rules don't come out until spring.
I know. Well,
It's gonna be
yeah, general. We can go based on this and then change it later, but it'd be a general idea. Yeah. So just thinner members because our bridge is pretty heavy. It's not extremely.
It's about 350.
It's 350. Might be a bit less because we're not using everything because we couldn't. I think you saw we had thicker members as well. Did you see them at our? Yeah, we had thinner ones and thicker ones. The thicker ones were meant for lateral, but it's to the point where we just can't connect them. So we can't really use them. And also, I think they are pretty heavy. I think they're very heavy, so they will cut down on weight, so that will boost efficiency.
Probably can be closer to 300.
Probably, yeah. So it is what it is.
Will the bridge be testable?
Testable, like
you assembled it and does it have this deflection that is different from the setup?
I mean, with the fact that our normal forces were like extremely over exaggerated, it shouldn't, like even with over exaggeration, it just hit 3 inches. But that was with like no members or like no rotational support at all when we're making the LinPro analysis. So in terms of like testable, it should be.
Yeah.
But of course, we're not at the stage where we can really tell that yet. But like based on what we have, it should be testable.
So
we're not optimistic that it will be.
Yes.
So despite all the challenges, like tomorrow, we want to see the bridge built as best as you can. We want to test as far as we can, provided it's safe. We want to do everything we possibly can for you to gain as much experience as you possibly can. And I think everybody here is going to help you go as far as you possibly can to learn as much as you can. So that's the point of it, right? So, yeah. Comments, questions?
No.
Good.
What else?
All right, thank you so much, guys.